times t plus v times dt dt. But that is dv dt times t plus v times, by the Furness-Ray equation, and truth be told, this is really the definition of curvature when you study it. We've got v kappa n. Let me rewrite this one more step here. So the formula for the acceleration is we've got dv dt times t plus v squared over r times n. Here, kappa is equal to 1 over the radius of the circle, the osculating circle. But t and n here are perpendicular vectors. So what's the length? You know, if I was to draw a picture of this, it would look like this, yeah? So this is A. If t looks like this, you know, if this is dv dt times t, then this guy over here would be v squared over r times n. My point to you is that the n direction and the t direction are perpendicular. So we have the Pythagorean theorem in this case. The length of A is what? The magnitude of the acceleration is actually the square root of dv dt squared plus v squared over r quantity squared. And this right here, my friends, is a formula for the magnitude of the acceleration as it relates to the speed at which it's traveling and the rate at which the speed is changing. But also this reveals that acceleration has two components. The one is center seeking for the, you know, the radius of curvature of the circle which the oscillating circle. And the other piece has to do with whether or not it's speeding up or slowing down. Right? So if you're going at constant speed, right, the only way you can be going in a circle is if your acceleration is pointing towards the center of the circle, just like that. Now I can derive that with other arguments that don't rely on the Furness-Ray equations, if you like, if I've got time. But anyway, any questions, I guess, is what I'd ask. No? All right. All right, so, oh man. Whoa, I couldn't do that again if I tried. It was spinning. All right. So, one final calculation for today. I want to look at just circular motion. Circular motion, constant speed circular motion. Let's assume that. Constant speed circular motion. What's that? How can we describe that? Well, if it's a circle, right? That means I can find a center of the circle. Let's call it R naught, right? And if the circle looks like this, right? If this is the oops, my bad. So I'm saying that that's the center of the circle. So here's my origin over here. If this is a position vector to the circle, can you guys tell me what's the equation the circle has to satisfy in terms of vectors? Like, what should I say? The length of R minus R naught equals to what? So R minus R naught is this vector, right? Is that right? If I add R naught plus the black vector, I get the lower, yeah, vector addition works, tip to tail, formula's right. So if it's a circle, what's the deal? R minus R naught has to be equal to what? What do we call the distance from the center to the point on the circle? The radius, right. So this has to be equal to, let's say, big R. And this is a constant, right? Constant radius. Because I'm assuming circular motion. Okay, great. Convert this to a dot product equation. How would you do it? How about if I square this, right? Square it. Then that looks like what? We have got r minus r naught dotted with r minus r naught equals to r squared. Now here, r is a function of time, r vector. This is function of time. So if this holds for all time, I can differentiate it, right? And what happens when I differentiate that? So you guys differentiate this with me, what do we get? We get d dt of r minus r naught dotted with r minus r naught plus r minus r naught dotted with d dt. Now I feel kind of silly writing these out because half the stuff I'm writing is 0, you know? What's the time derivative of r squared? Thank you. By the way, what's the time derivative of the constant vector r naught? Also what? 0, right? Differentiate a constant vector, you got 0. I'm not letting the center of the circle move. We're talking about a fixed circle, okay? If the circle was moving, then that derivative would be non-trivial, and we'd pick that up through the calculus right here. But it's not, we're assuming not. So what are we left with? This is velocity. So what we have is velocity dot r minus r naught plus r minus r naught dot velocity is equal to 0. In other words, twice the velocity dotted with r minus r naught is equal to 0. Does that make sense? What is this? What have we just derived? What's it say? So therefore, the velocity is perpendicular to r minus r naught. Does that make sense to you guys? Should the velocity be tangent to the radial vector for a circle? Yes, that is what r minus r naught is. It's the radial vector. It's the vector which points from the center of the circle out to a point on its radius. Okay, so differentiate again, what happens? What happens if we differentiate again? We get 2 dv dt. Let's drop the 2. Drop the 2. Drop the 2. So we get dv dt dotted with r minus r naught plus v dotted with, well, let me get straight to the point here, dr dt, because the derivative of the r naught is 0, right? That's equal to 0. Which is to say that the acceleration dotted with r minus r naught is equal to minus v dot v, right? In other words, the acceleration dotted with the, let me call it r hat, is equal to minus v squared divided by r. So I'm introducing r hat here as like this thing. This says that for a constant velocity circular motion, right, at least the radial component of the acceleration is what? Minus v squared over r, right? But if you drop back to my other derivation, we see that that's in fact the whole deal. Because, what? The acceleration, generally speaking, oh man, I erased it. Oh, it's still here, kind of. So you see that, oh man, I wish I left that equation. Oh well. We had this formula, right? A was dv dt times t plus v squared over r times n, right? So we're given in my last example here that this is 0, which means the acceleration is equal to v squared over r times n. Notice that there's no minus in this because the normal vector is center seeking, whereas r hat points out. So these equations are consistent, but for circular motion, constant speed circular motion, the acceleration is simply v squared over r, right? So You probably can derive some of this stuff without the Frenet frame, but I think it's good for you guys to see the Frenet frame. There's like a section on it in Stewart if you want to read more. And if you're interested in much more, ask me. I can send you some notes and junk. But that's all I got for you guys today. So I hope to not see you again. I usually have a meeting at this time, so.